Alright. This is going to be episode number 23, the final episode in our video series journey going from a noob to an ASM coder. The very final episode. Alright, what are we doing today? We're doing all about bit rotation. This is going to be a long video, probably about 30 minutes in length, maybe more. It's going to detail some of Broadway's very complex instructions that you really need to know to really cut down on a ASM source and to do very complex situations. So all about bit rotation. So you may have seen, well, you definitely have seen an instruction like this. This is a bit rotation instruction, okay? And there are three forms. Copy paste that. We have rotate leftward, then and with mask. Rotate leftward immediate, then and with mask. And then finally, the most difficult to understand, rotate leftward immediate, then insert mask. And when the term and is being used, it means logical anding. So if you don't know what logical anding is, you can look up about logical operations regarding anding, ORing, XORing, NANDing, and whatnot. Okay, so remember what I talked about in previous episodes? I mentioned this a couple times about binaries. So essentially you have hex, decimal, and registers, like so. They're actually binary representations. They're readable binary representations, okay? So it makes it a little bit easier to read numbers, because if you did everything in binary, it'd be insanely difficult. So essentially what we're doing is we're going like a lower level than plain Jane ASM per se, the lowest level possible, which is just binary, 0 and 1, that's it. So going back to these instructions, these bit rotation instructions, they're like PowerPC Swiss Army knife. You can multiply, divide, shift, rotate, clear then shift with these instructions. You can check for negative values, alignment, check if a number is divisible by another number. The possibilities are basically endless, so this is why it's really important to know these instructions, but they're so difficult to understand that even like other normal developers and programmers, like real programmers and stuff, you'll see them on forums on like things about PowerPC. They'll ask about, well, I don't understand about these bit rotation instructions. So once you understand these, your knowledge in ASM is going to increase by a drastic amount. So just keep in mind, we have three different kinds, okay? These are standard mnemonics. However, we have simplified mnemonics for each of these three instructions. Dolphin will display all of these instructions always in standard form, never in simplified form. Okay, but first let's go over binary and what it is. So here's a hex value. First, you might want to take some 15 minutes or so to Google a quick binary tutorial and what it means. The one thing I will say is that, remember I stressed a lot that you want to learn hex. And the reason I say this so much is, for one, you're working a lot with memory address values that are shown in hex in the registers, obviously. But second is, it's so much easier to convert hex to binary and vice versa. It's way too difficult to do it with decimal. And you'll see why here in a bit. So that value in binary is that. I'll give you a chance to take a look. Okay, so this is why hex is easier to convert to binary and vice versa than decimal. We can put all these binary numbers in groups of 4, slots of 4. So this is the group representing 1, this is 2, and like over here, this is C, this is D, and whatnot. Keep in mind, registers, I know this is kind of sounds silly to mention this, but registers are always 32 bits. Just because the value is 0 doesn't mean no bits exist. It just means the bits are all set to 0. Okay? So another thing to know, we have bit 0, the first bit, and it goes bit 0 to 1, 2, 3, 4, etc., till we get to bit 31. So 0 through 31. Bit 0 is also called the sign bit, because all negative numbers have their first bit 0, their bit 0 as 1. And another name for the sign bit is the most significant bit, because it's the first bit when you're reading from left to right. And then the final bit, bit 31, is the least significant bit. So now that you understand some of the terms and how you convert hex to binary, we'll cover basic clearing instructions. Now, we've gone over this first one before in a previous episode, just briefly. Clear left word immediate clears all the left-hand bits. Excuse me. And clear right word immediate clears all the right-hand bits. The XX value is a decimal value, which you represent how many bits are going to be cleared. Source register, obviously, and the result, the destination register. Pretty self-explanatory. This is a simplified mnemonic for this second one right here. Rotate left word immediate, then and with mask. So clear left word immediate and clear right word immediate. So let's test out. Let's do a clear right word immediate. Let's say we have R5. And R5 is that in hex. Okay? And we want to execute this instruction. Alright, so first you want to transform that to binary. Like this, okay? And when you're doing clear left word immediate, you start from the left and go over how many times this number is here. So it was like clear left word immediate 3, you just go over 3. But we're doing clear right and we're doing 22. So we start from the right, go 1, 2, 3, 4, 8, 12, 16, 20, 22. And what does clear mean? Clear means set whatever bit it is to 0. So keep in mind, this is our hex value for R5 beforehand. We're going to clear all these bits on the right side. 5, 6, 7, 8. Thus, R5's new value is, copy paste, is this. Notice how like the AB changes to A0 and the F is gone? Just because when we take this new thing, this new binary numbers, and we do all groups of 4, convert it each group to hex. This is 1, this is A, this is 8, and the rest is zeros. And then clear left is obviously you just do the left side. So pretty easy to understand. Okay, to the next chapter. We have basic bit shifting, simplified mnemonic. You have this, and you also have that, but you can also have this. Really simple. Left is for left, right is for right. For the immediate, you'll have a value, anything from 0 to 32. I also want to mention the clearing instructions. Obviously, you can only work from 0 to 32 because you only have 32 bits in a register. You just write this in decimal. It's a low number. I don't see the reason for writing this value in hex. And source register, result, destination register. The shift left word or shift right word is just slightly different because instead of using a value for the bit shifting, you use a value in a register. Obviously, that value in the register has to be arranged from 0 to 32 or 0 through 20 in hex, or it'll be an invalid instruction and you'll get a compilation error. Okay, so let's say R5 has this value. Okay, this is the value in hex. Okay, convert that to binary. Boom. Alright. So if we execute this instruction, every bit gets moved to the left. Now you're probably wondering, well, what happens if something goes past, or excuse me, this is a shift to the right. With this shift right instruction, everything gets moved from left to right, okay? From left to right. And it gets moved over 15 amounts of slots, 15 for 15 bits. Now you're probably asking yourself, if we're moving to the right, what happens if we go past bit 31? Well, anything that goes past bit 31 is just thrown away. It's gone forever. And you're probably asking yourself, well, what do we do about the numbers that are supposed to come from the left or going to the right, but there's nothing beyond bit 0, obviously. They just get appended with zeros. So if you do this and follow what I say, instruction turns, or value turns to this. So look at this guy right here. If we do this and count to the right 15 times, he ends up here. Everything else is thrown away because it went past bit 31 when shifting to the right. And the rest of the stuff gets filled in with zeros from the left-hand side, being moved from left to right. So thus, the hex value changes to 1. And to the left is just the opposite deal. Things that go left past bit 0 get tossed away, and from bit 31, from the right-hand side, things get appended with zeros. Okay, makes sense? Okay. Disassembling the standard mnemonics. Because Dolphin does all bit rotation in standard mnemonic form, if you were to write a code using simplified mnemonics of the bit rotation, it would be tough to view in Dolphin. So let's disassemble these instructions per se. Okay, so you guys know this is source register, destination register. This is called SH. If you're reading various PowerPC PDF files and whatnot. So what we do is we rotate to the left. This is the amount in decimal. We rotate the amount of bits we rotate to the left. Now rotate is different than shifting. Here is a good graphical representation of shifting versus rotating to the left. As you can see, with shifting, if something goes past, an imaginary bit placement, it gets thrown away and the rest get appended with zeros. And the stuff in the middle shift accordingly. Rotation left, rotating to the left, things never get lost. It's like a counterclockwise spin. So if you have a 1 in bit 0 and we're rotating to the left by 1, it gets moved all the way to bit 31 and all the other bits move along accordingly. So this value here is always a left rotation, never a right. So this is the amount of bits you rotate to the left, okay? Once you have this temporary value after you rotate to the left, you then do a logical AND set by these numbers, okay? So this is mask begin, MB. This is mask N, ME, mask N. So essentially, we'll just show an example really quick of how what the mask looks like in hex form, or how you can visualize it, and how we can take values and rotate them and how they change. So let's just use an example without explaining too much further. Actually, let's go ahead and explain the mask. So the mask means mask beginning, mask end. Mask means set the bit to 1. So if we have this mask 0 to 28, we go from bit 0 to 28. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. The rest is zeros. So you can also write this in hex. So instead of having the 0, 28, you can replace these entire two numbers, including the comma, replace all that junk with this. So depending on how you like to do your bit rotation instructions, you can use the range, decimal range with the comma, or you can just put the whole hex number. So what happens is, whatever number we get from rotating the bits by 3, we logically AND it with this. And what is AND? What is ANDing? What does that mean? Well, you want to do this one bit at a time to make sense. So what it means is you compare the bits from the rotation after this, and you compare it to the mask. So let's say we have a bit in the rotation value, the rotated value, excuse me, and we have the bit in the mask is 1. That equals 0. Now if we look at another slot, and the bit in the rotation value is 1, but a bit in the corresponding mask is 0, the result is still 0. They have to be both 1s for the result to equal 1. So that is how you would logically AND stuff in a binary level. But chances are you can just use a logical operation calculator to make life easier. Okay, so let's say we have this instruction. Alright, we know about the mask value. We know it's all F's and an 8. So let's say we start off with this instruction. Okay, not instruction, this value in R5. Okay, so here we go. That's the value before rotation. Rotate it by 3, we get this value. Like for example, take a note of this 1 right here. It goes 1, 2, 3. So thus, if we change our rotated value in hex, we get this. We'll put it right here, like this. Now what you do is you take the mask and you logically AND it. Like this. And if you logically AND 0, remember what I said, 0 and 1 is 0. 1 and 0 is 0. The only way you can have a result of 1 is you have 1 and 1. 0 to 1, 0. 1 to 0, 0. 1 to 1 is 1. So if we do all these calculations, this hex result changes to this. Boom. Because what happens is, this is still, these all remain 0, this remains 1, these all remain the same, except right here. Look at this guy. 1 and 0 changes to 0. Thus, this group of binary changes the hex representation from C to 8. So this is our final result. A lot to take in, but just take your time with this thread. And if you get rotate leftward, then AND with mask with no immediate value, this value will be represented by like a register, like R3. Obviously, if the register value is not in the range of 0 to 32 in decimal, you get a compilation error. Okay, so this next one is very tough. I'm gonna get a sip of water. Okay, so now you understand about rotating to the left. You understand about how logical ANDing works at a low binary level. And you understand about mask beginning, mask end. Let's talk about the most complicated rotation instruction ever. Rotate leftward, immediate, then mask insert. So there is no logical ANDing in regards to how this mask works. Okay, so really we just got to dig right into this and get started. Okay. Source register, destination register, how many times we're going to rotate by the bits, and then the mask beginning, mask end. But keep in mind, we're not going to use the mask for logical ANDing. It's going to be something different. So let's see. Let's say before the rotation, R4 is this. Alright, this is R4 before we rotate the bits by 2. Alright, we go ahead and rotate the bits, then rotate, and we're left with this. Okay, now let's go and put this binary representation is this. Okay, so this is R4. R4 rotate. Okay, now let's look at our mask. Okay, our mask in hex form, because we're doing 0 to 29, is all F's and a C. But we'll just go put it in binary so you get a better representation. You see, bit 28, whoops, bit 28, bit 29, bit 30, bit 31. So that is our mask. Now, what do we do? Okay, we got our rotated value, we got our mask. We don't do logical ANDing, so what do? We need to look at R6 original value before this instruction gets executed. So let's say R6 has this value. So you guys should know that equals FFFF, or 4 zeros and 4 F's. Might as well put the zeros in. Okay, so there you go. What do? Okay, so this is really important to understand. Okay, with our mask, okay, so you gotta look at the mask. If a bit in the mask is 1, then whatever bits are in our rotated, this is after rotation, rotated R4 register will replace the corresponding bits, whatever bits are in R6. If a bit in the mask is 0, then those bits in R6 are unaffected. They're preserved. They are not replaced by the bits in rotated R4. So what does this mean? Okay, we have bits 0 through 29 in our mask. That means these bits right here will be copy and pasted. Alright, they replace the corresponding bits in R6. Backspace, paste. Then, if the bit in the mask is 0, bit 30 and 31, We do not use the 0 to 1 from the bits in the rotated R4 for bits 30 and 31. We retain R6's value. Thus, R6 now equals this. From 4 zeros, 4 F's to this. That is how rotate leftward immediate then insert mask will go. If you had a situation where you had the source register the same as the destination register, when you just change this to this per se. Alright? If R4 was original, like somehow, but you get the idea. The point is, if source register is same as the destination register, you got this value, just keep it at the bottom like this. Do your rotation of R4. So R4's original value gets put to a temporary value after rotation. So you take R4's temporary rotated value with the mask, and then you do the mask comparison whether or not you replace the bits with R4's original value. If that makes sense? So that's how you would do it if the source register is same as the destination register for a rotate leftward immediate then mask insert. Okay, so to show that's a real instruction and it works in Dolphin, I was using this instruction earlier when I replace instruction. Whoops. Where's this at? Okay. So this is our instruction we just went over on the tutorial just a second ago. Okay. So let's go ahead and just put junk here. A. Okay. Alright. Let me get our original value. So for this instruction, we've just plugged in the Dolphin just one step ahead. This is the value, okay, our original R4 value. So you can see it's right here. No, there's no gimmicks going on or anything like that. Go back to code view. Alright. And my bad, it actually doesn't matter. I almost forgot that. Good thing I didn't, or else I have to redo the video. Okay, so obviously we have R4's value here. We have R6's original value here from the example, the OG value, because the destination register's original value affects this instruction. Remember that. Okay, so now we got this here. Bring that here. We'll scroll up a bit. Okay, now watch. Here we go. Look at R4, original value. Look at R6's OG value of a half word of F's that we just showed in the example on the text editor. And boom, look what R6 changes to. Copy, paste. See that value there. Just put a bunch of spaces. And boom, as you can see, the same value. Just capital A, lower a. But same exact value to show you that this is a real instruction and I actually know what I'm talking about. Okay, and then we have a simplified mnemonics list. Just a big reference list. You can use simplified mnemonics, but obviously keep in mind Dolphin shows standard mnemonics. There's also a little chapter you can read, just a quick explanation of how Dolphin shows the mask value like incorrectly when it's trying to do a hex representation form. Don't know why Dolphin does that, but just keep that in mind. And then chapter 9 in the thread, which you want to look over, is just a lot of good examples, okay? So that is it. That is the final episode on this whole deal. Episode 23 is over. You are now a veteran ASM coder. You have completed the journey. Give yourself a pat on the back. I know it's a long one. I don't know how long it took you. Forever who's viewing this at the moment. Could be some days. Could be weeks. Some weeks. Could be months. And that is it. Please visit mkwe.com. The first ever site, and I still think the only site to have an organized, centralized database of every publicly released MKWe code and whatnot. We have all sorts of PowerPC guides, soft modding guides, Dolphin guides, and some stuff about AltWFC, general discussion, all sorts of ASM and Gecko resources, and various stuff. And that is it. The end of your journey. Congratulations.